So as we go, if we look back on the first two lessons, the main idea of the first two lessons was the probability calculation equation, which is number of possible outcomes for some event and number of favorable outcomes for a particular event, and you calculate the probability. Now we're moving on to the different ways we have of basically understanding what the number of possible outcomes and the number of favorable outcomes are. And the tool that we focus on for the next two lessons is the Venn diagram. And Venn diagrams basically show the sample space. So we have the sample space, which we normally show as a rectangle. And then we have specific events, which we show as circles. So sometimes we'll say, well, we'll often say the sample space S and the event A in the sample space. And so some terminology that you'll see me talking about and you want to get used to is the sample space is basically the number of, shows the number of all possible outcomes. Okay, every possible outcome that's possible is shown in the sample space. An event of a random experiment is a subset of the sample space. So A would be an event in the sample space. Now, it's possible to have what's called the union and intersection of two or more events in the sample space. So if I drew another event B, that is another event or subset in the sample space. And it's possible for something to happen which is both in the event A and the event B. And that would be this region over here. And the way we would describe that would be to say it's A and B. It's in both sets. Or using the smile notation, it would look like this. Okay, so that is, and we call that the intersection because it's where the two circles intersect. However, there is another word that you have to be familiar with, which is union, and union is, oops, I just made the A disappear. Union is when we say, well, the set A or B, and A or B, if we were looking at it in terms of the drawing, wouldn't just be the area where they overlap. It would be everything which is in A or in B. And we call that the union of two sets. And we can also write it like with a smiley face between those two. Okay, so that's, you're going to see this notation come up in the lesson today. The other thing that we have are some identities. So in Venn diagram notation, if the two events do not overlap, so say we have something like A and B, what are those two events? How do we describe the relationship between those two events? I'm curious to know if you guys have seen this from class. So that would show a relationship between two events. What is the word we would say to use to describe their relationship? And it's in the little thing on the screen, but I want to know. Tanda, let's go to you.
Is it not mutually exclusive?
Yes. So the events A and B, perfect, Tanda. So we say the events are mutually exclusive because they have an empty intersection. They don't intersect. There's no element which belongs to both A and B. There's no outcome that's possible to be in both A and B. Another word we use is disjoint, but normally mutually exclusive is the event that we use. Okay, so that's another word that you'll see come up, and basically it just means that if you're in A, you can't also be in the event B. And then there is something else called complementary events, and complementary events basically look, they probably look something like this. Maybe that's a better way of describing it. Or if I use the circle notation, it would be, here's A, and outside it is A dash. And complementary events are mutually exclusive, but not only are they mutually exclusive, they add to this whole sample space if you add them together. So you'll notice that A and A dash take up the whole region of the rectangle. And complementary events have this property. You can write it like this, or you could say it like this. The sum of the two of complementary events probabilities is 1. Okay, so that is another sort of idea that will come up in the lesson. And then there's one other identity which I just want to point out. You don't have to memorize it, but the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And that is something which comes up. It's called the or the additive identity. And that relationship comes up. The other way of writing it is to write it in terms of N. And if you're a little bit like going, why is this man using so many symbols? I hear you, but I just want to put it in your head a little bit now at the beginning. So you can sometimes see it written like that. And this identity is kind of helpful in certain questions. Okay, so I've thrown a lot of theory at you at the beginning. In all honesty, the easiest way to learn the section is doing examples, but I just want you to think about these words as I refer to them in the lesson. Okay, give me a quick thumbs up if you feel like you've broadly are with me. Give me a thumbs down if your head's spinning and you feel like you've died by symbols. Okay. Apologies if you do feel like you had death by symbols, but it's kind of better if I get going and say some of them and then refer to them as we go. Okay, question number 1. There are a group of 27 girls, 10 play netball and the rest do not play netball. I want you to answer the questions for me, A to D. There's a drawing also of a Venn diagram. You won't be able to put that in the chat, but everything else I want you to try and put in the chat. So try and answer this question based on what you know of Venn diagrams. If you feel like you have no knowledge of Venn diagrams, please let us know in the chat or raise your hand, and we'll go from there. Okay, yes. How many in the group of girls do not play? Well, 10 play and 27 is the total. So that must be 17. And if I choose this as my N and this S is my sample space, then this is going to be 10 and this is going to be 17. Yeah. So the Venn diagram, I mean, is fairly, it describes what's going on. So that's those two. What about C? Are the events play netball and do not play netball complementary? Loretta, why are they complementary? What are the two things you were looking for? So Loretta said they are complementary. Mason said the same. Essentially, we could say that these are N dash, or they don't play netball. So the two things we're looking to see is that there's no intersection, there's no overlap, and do they fill the whole sample space? And so the answer is yes, they are complementary. So their intersection is empty. The way we would say that, if we really want to be fancy, so the intersection of N and N dash is empty. So that's good. And n plus n dash, sorry, the probability. So I'm just throwing in some fancy notation because you guys get the problem. Their intersection is empty. There's no overlap. And their probabilities add to 1. Or that's another way of saying it. Okay, what is D? N of S. What is N of S for this question? So N means S is the sample space. So how many items are there in the sample space? There are 27. Yeah, let you, absolutely. Because I've just gone 10 plus the 17. Okay, what is the probability that one chosen girl plays netball? So that's EI. And then what is the probability that a randomly chosen girl does not play netball? So I'm looking for now remember, whenever we calculate probability, we have number of possible outcomes on the bottom, number of favorable outcomes on the top. So how many possible outcomes are there? Well, because the set has 27, it's 27, 27. What's favorable if we say, what's the probability of playing netball? It's going to be 10 out of 27. What's the probability of not playing netball? It's going to be 17 out of 27. And because they are complementary events, you'll see that if you add those two probabilities together, you get 1, which is what I was saying earlier on. So you could have actually found the probability of P n dash by just going 1 minus the probability of n. So 1 minus 10 over 27 is that, which gives you 17 over 27. Okay. Thumbs up if you're feeling good. Thumbs down if you're feeling a bit overwhelmed by the pace. Let me see your sentiments. Since I can't see your lovely faces, okay. Cool. Well, then what I think we need to do is we need to go on to a part 2 question. Now, let's talk through this a little bit before we get started. And I will get rid of this example here. So it says 24 learners in a class were invited to Adam and Nisha's birthday party. Now, there's still only 2 events. When we start to look at this question, there's a lot more words going on, but there's a couple of key ideas. And what are the events is one of my main considerations. So Adam and Nisha's birthday parties are the 2 events. So I'll probably end up calling them like the sets or the events A and N. Then I'm looking to think, look, I know that probably I'm going to have to draw a Venn diagram at some stage. And so I would suggest that even though this question says draw a Venn diagram only in C, I would start to draw a Venn diagram earlier. And then once you draw your Venn diagram, you can then try and answer these questions. Now, when you draw your Venn diagram, you've got to make some decision. You've got to decide if are there students that went to both, or are there no students who went to both? Because if there's nobody who went to both, your circles will be like that. Whereas if there's somebody who went to both, the 2 events will look like that. Now, it says, okay, it's actually kind of hard at this stage. It says 13 went to Adam, 12 went to Nisha, 3 learners decided to not go to either of the parties. So do you think, should I ask, yeah, let me do this. Do you think there are some students who went to both parties? That's what I want to ask you guys. How would you figure that out? Because our Venn diagram is going to be affected. If there's somebody who went to both parties, but at the moment, it's not clear how that would work. And so I might have to use an identity from earlier on. So A, so I think it says 3 learners. Okay, this is actually quite a sneaky one. So are you guys saying there are no students who went to both parties? I think there are students who went to both parties. So let me show you my thinking, and then you will go from there. Okay. One of the things is I see that there are 3 learners who did not go to either of the parties. So that makes me think that there are 21 learners. So if I go 24 minus 3, there are 21 students who went to either A or N. Give me a thumbs up if you understand how I got the 21. So 3 learners decided to not go to either of the parties. So what we know is that if we imagine there are some students who went to both, there are 3 students out here who didn't go to either of the parties. And now there's Adam and there's Nisha. Now it says to us that there are 13 there should be inside the circle, there should be only 21 students in total. However, if I add up 13 and 12, I get to 25. So 13 plus 12 is 25. And the reason I get to 25 is there's some students that I must have counted twice. So think about that for a moment. So if I said 13 students went to Adam's party and 12 students went to Nisha's party and there was nobody in the middle, can you see that the number I've got is too big? So the only way that the 21 can work is if some of the students are going to be in the middle. Now, there should be 21 students and in the middle, and there at the moment is 25 if we keep them separate. So what you're going to find, I'm going to use this identity. The number of students in A or B, or I'll say A or N. So just watch this. So A or N, we'll call this N, and then this will be A and N. So we know how many students are there in A or N. We know that there's going to be 21. So that is standing for this whole region over here. It's 24 minus 3. Okay, so that region is 21. How many students are there in A? We know that there are 13, and that comes from this. How many students are there that are going to Nisha's party? There are 12. Okay, and then the last bit is going to be the number of students that went to both parties. So whatever this is, I'll call it X, is going to be the number of students who went to both. Can you find out what X is for me? Can you find out what the number in the middle is? Okay. So if you move the X across and you move the 21 across, you're going to get 4. So there's 2 ways that you could have worked this out, guys and girls. The one way to do it is to say, look, if I add up 13 and 12, I get 25, and that is 4 too much. And if that's 4 too much, there must be 4 in the middle. The other way of doing it is to use this identity called the OR identity, which helps you here. Either of those will work. And you might have to look at this example again to get it, but that's the thing. Now, how many people are going to be in A with the question mark that I've left there now? Because we know 13 went to Adam's party. So what is that going to be now? Okay, so that's going to be 9. And then what's going to be the number of people who only went to Nisha's party? So we know it was 12 and then 4 plus what? So that will be 8. Okay, fantastic. Now that we've done that Venn diagram, I want you to find me the probability that a learner only goes to Adam's party. So what I would call the probability of A only. So I'll just say A only. And the probability he goes to A and N. And then what's the probability he doesn't go to either of the parties, which, so I'll say in notation, what would that be? Okay, you can start working on those. So it would be, I'll just say not either for now, or using fancy notation, it would be A or N complement. So this is the same one. So A only is going to be 9 over 24. Then A and N is going to be 4 over 24. And not A or N. So basically, what I'm doing with this fancy notation is I'm saying A or N is the circles inside. I want everything outside. So the dash is not. And so that would be 3 out of 24. Okay. So that was a more tricky example where you had to use the additive identity. And I hope that gave you a sense of how you can use it. The additive identity, the reason it works is that if you imagine counting this circle, if you counted A and you counted N, the problem is you've double counted. So if you want to say, now tell me how many items are in both these circles together, if you've counted 13 plus 12, you've counted 4 twice. And that's why you have to subtract the intersection of the two. But that needs quite a bit of practice before your brain really gets it. I want to squeeze in one more before the break. Can you give me a thumbs up if you're with me? Give me a thumbs down if you're feeling a bit, yeah. And be honest, don't worry. Yeah. Okay. I think we can squeeze in. Let's just do this bit at the top here. We're not going to do the whole question. We are just going to do, I want you to do A and B for me. So we're ignoring this. And what you're given here is you're given 100 students who are being surveyed, and 69 students have an older sibling or an older brother or sister, 41 have a younger sibling, and 25 have both. The Venn diagram shows this information. I want you to try and answer these questions for me. Let's do that. So no siblings, I guess, can't be in either of these circles. It must be this region here. So what's that going to be? I get 15. So this is 15. What about determine the probability of an older sibling? So what is the probability of O? What is the probability of PY? Probability of O and Y. And then what is the probability of no siblings? So no siblings would just be O or Y dash. Or you just say probability of no siblings. I'll give you some time for that. So the probability for an older sibling is going to be, well, all of these are going to be out of 100 because the sample space is out of 100. And the probability of choosing an older sibling, having an older sibling, is actually going to be 69. Because when I say, what is the probability of choosing an older sibling, I count the whole circle. So these 25 have a younger and an older sibling, but that doesn't matter for my question. I'm interested in, are you in the circle of O? And so it would be 69 out of 100. The probability of being younger, for the same reason, having a younger sibling, is 41 out of 100. Now, what's the last two? So what's the probability that you choose a random student and they have both an older and a younger? Then they're only going to be the ones that are in the intersection. They're only going to be the ones that are in both sets or in the unhappy face, if I was using this notation. And then have no older siblings is basically the complement of basically the two circles. Anything which is outside the two circles, what's that going to be? It's just going to be 15 out of 100. Now, what's really cool to show you is that the OR identity that I showed you earlier on in the lesson, just to show you here, the probability of, oh, I didn't actually work out the probability. Let me add one more thing. Let me add, what is the probability of O or Y? What's that probability? So what is the probability you have either an older or a younger or both? So older or younger or both. It's still going to be out of 100, but now it's 44 plus 25 plus 16. Or you could just go 100 minus 15. Now, watch this and be amazed. If you imagine taking this one. So that one over there is equal to, oh, how am I going to write this? So basically, if you take 41 over 100, which is plus 69 over 100 minus 25 over 100. All that I've done there is I've taken the probability of O, probability of Y, minus the probability of O and Y. I want you guys to work out what you get for this. What is 41 over 100 plus 69 over 100 minus 25 over 100? And you should be getting 85 over 100, which is the same as this one down here. And so that's just to show you that the OR identity also holds with the probability identity there. Okay, I have pushed you guys hard. It is time for a break. So I want those cameras on and I want to see you stretching. I want to see you just giving your body a break. So up on your feet. Sir, are the events complementary? Older and younger are not complementary, because they have an intersection. There are 25 students who have both older and younger. If events were complementary, there can be no intersection and they must fill the whole sample space. Okay.
Come on, guys,
Tonight,
please put your cameras on. Give us a
I'll
good
turn your cameras on.
face.
Okay.
I'd love to see your faces.
Yes.
You guys have been doing such hard work. You deserve
Let's
this break.
multitask, and then let's stretch it out, and then I'll answer Tanaka's question now.
Shout out to Mason, Nadi, Anjo or Anjo, I'm not sure. I'm sorry. Shout out to Siam Tanda, Shisana. Yes, guys. Loving
guys.
this energy.
Stretch it out. Oh, I can feel the joy through the internet.
Your body will thank you.
You. Yeah. Thank you for taking care of me. Oh, that's what my body says. It's like, oh, thank you.
Getting ready for the second half.
So Tanaka has asked, can you write the answer in decimals? So Tanaka, you can. Normally, the only reason, like, I wouldn't do any extra work unless you have to. Decimals are really good for comparing which probability is more likely. So it's absolutely fine to write it as decimals, completely correct. But generally, if I've written it as a fraction, I just leave it like that, unless I'm comparing. Then if I'm comparing, it's much easier to compare with decimals. Okay. Now, before we move any further, we first have to have a brain break. And so here is your brain break. And while you're doing that, I'm going to stretch some more because my body is saying, please just stretch some more. Okay, what do we think the answer is for this brain break?
Mr. S, just to interject a little bit with regards to Kevin's question, we're not really doing third term work, are we? Are we just covering the whole syllabus, not really following the school?
No, we are. So a lot of students, we basically third term was measurement, data, probability, and then finance. Some schools will do finance more under exam prep, but we are basically covering roughly the CAPS progression. But schools do it slightly differently sometimes. But yeah.
We are doing third term work right now.
Yeah.
Thanks,
exactly.
Mr. A.
Okay. Tanaka, I think you're on the right track there. So if you imagine the numbers 1, 2, and 3, 1 plus 2 plus 3 is 6, and 1 times 2 times 3 is 6. So, Tanaka, you are indeed correct.
Well
the number
done,
is
Tanaka.
1, 2, 3, and Katlego. I see you also got that.
Go, Katlejo. Yay.
Yes. Does that make sense? Okay, I really hope that you have had a good stretch. Give your body what it wants. So have a stretch if you need, and then we're going to move on to the next question. So what I want to do is sometimes Venn diagrams are written as probabilities instead of numbers. And so I just want to do a question where you are doing some probabilities. So let's try and do this one and then see how it goes. So instead of giving you the number of students, they're giving you the probability. And I would start by drawing a Venn diagram, and then we'll go from there. So there's only 2 events. And so just like last time, because there is going to be an overlap. Because we know, because let's just say maths is this and geography is this. The probability that neither of them, or he takes neither of the 2, is 0.2. And so that is going to have to be outside the Venn diagram. So this is going to have to be 0.2, because that's the probability that. Now, can you use that hint? And can you build from the last one to think about the other bits? So at the moment, Kevin, we're only looking, we're doing the Venn diagrams not in terms of numbers, but in terms of probabilities. And so all the regions in the Venn diagram have to add up to 1, and so I've just said the probability that he takes neither of the 2 is 0.2, which means this region over here must add up to 0.8. However, at the moment, they've just given you the probability of maths by itself and geography by itself. And so you have to use a little bit of like asking yourself, if it should be 0.8 and I'm adding up and I get to, and I add them together and I get a bigger number than that, what is this middle bit going to be? Yeah, Nadi, let's go to you.
So I wanted to ask a question. Why should it be 8? Why should it add up to 8?
Why should it add up to 8? So if you think about the 0.2, okay, so the probability that he takes neither of the 2 subjects is 0.2. So Nadi, would you agree with me? You can show in the chat if you want. The 0.2 is outside the G and the M, which represent geography and maths. So inside, there has to be a probability of 1 or 100% that either they take maths or geography or nothing. And or neither of those 2. So if you go 1 minus 0.2, you get 0.8. It's almost like the 2 circles together are the complement of the region outside. Now, what I was thinking is, Inam's asked the same question. So basically, if you imagine the regions in this question, the 0.2 region is everything in the rectangle, but not in the circles. What I'm then saying is inside the circles, must add up to 0.8 because together I must get up to 1. So I just went 1 minus 0.2 to get the 0.8. Now, the problem is that I'm told already that maths by itself is 0.7. So maths, the probability of maths is 0.7, and the probability of geography is 0.3. Now that already adds up to 1 by itself, which is greater than the 0.8 that I know it has to add up to. So using the same trick as last time, what's this middle region going to be? It's actually going to be 0.2. And then the question is, what are these two regions going to be? Well, I know geography in total is a probability of 0.3. So this has to be 0.1. And then what does maths, the people who only take maths, going to be? What's that going to have to be? So if I know in total it's 0.7 and I've already got 0.2, this has to be 0.5. Exactly. Now, if I want to answer this question now, what's the probability he takes both maths and geography? That's going to be the region in between, or the intersection. So that's going to be 0.2. What's the probability he takes only one of the two subjects? Now, only one of the two subjects is actually going to be, it's a little bit, I can't get the intersection. So I want that bit and I want that bit. So what's that going to be? What's the answer going to be for B? He takes only one of the two subjects. So the answer is going to be 0.6, which is this region here. So that was an example of a Venn diagram where, again, we're using this idea that of the OR identity, or the double counting, but instead of the Venn diagram being in numbers, the Venn diagram is in probabilities. So just give me a thumbs up if you broadly understand how that works. But if there are questions, I want to answer them now. So I think there will be questions. And so let's give a moment for students to ask questions. Okay. So I see a couple of thumbs down. I'd love for those students to point out where I lost you. I suspect it's probably around the 0.81 and where the magic 0.2 appears in the middle. I think that's the case. And what I'm going to suggest is, if you just, what I basically did was I said, look, I went 0.7. Oh, what am I doing? I went 0.7 plus 0.3 for the probability of maths and the probability of geography. And then once I did that, I got 1. But I still had to subtract the probability of basically the 0.8 that I got already. That was the true, how would I count it? I'm basically taking 1 minus 0.8 to get that 0.2 in the middle. Can I suggest that because we record this, you re-look at this again and just work at how I got that 0.2, because it's not going to be an efficient use for me to do that. Boy Tumelo said, how do I get the 0.6? Boy Tumelo, the green bits are the 0.6. So those are the regions that, if I had included the 0.2 in the middle, those students do maths and geography. And the question says he only takes one of the two subjects. So that's why I only add up those two. Okay. Right. So again, I really encourage you to re-watch these videos. If you are unsure about something, let us do one more like this. Let's do this one. So let's go like this. Okay. This is your question. There's a group of 69 students, 41 take mathematics, 25 take history, 12 choose neither. If I select a random student, what is the probability that the student does not take history? See if you can solve that question. You can do it.
Yes, you can.
I'm just trying to think, there might be another way that we can actually do this. Let me just experiment. So we know there's 12 out here because 12. So I actually thought of another way that we can do this, but let's just see how we go. So the other possibility is you could also make this X, and then you could make this 41 minus X, and then you could make this 25 minus X. And then that might help you solve the X that might help you solve in another way. So that's the one possibility. I hadn't actually shown that earlier in the lesson. Or what I would do is say, I know that if there's 12 outside, how many should be inside? 69 minus 12. Let's go. 69 is going to be 57. And at the moment, if I add them together, 41 plus 25 is 66. And so that is basically is going to mean that this has to be 9. So let's have a look. So make sure I'm right. 57. So 66. So this is going to be 9. In which case this would be 32. And this would be 16. And let me just check that because I'm rushing now a little bit. So if a student is selected at random, so this is history and this is mathematics, and does not take history, so it would be 32 and 12. So it would be this bit here, and then also this bit over here. Now, which would give you a probability for this one of 32 plus 12 over 69, which would be 44 over 69, which would be the answer. Now, I did that a little bit quickly. That the top one was the method I was using throughout the lesson. I just thought of this one now. You could also solve for X like this. If you did it like this, let's just see if we get the same answer. We should. 41 minus X plus X plus 25 minus x plus 12, what is that equation going to have to be equal to? What's that equation have to be equal to? 41 minus x plus 25 minus x plus 12. What is that going to have to be equal to? It has to be equal to 69 because it's the whole sample space. That's the 69 up here. And so if we add this up, minus x plus x goes away. And then we get 41 plus 25 plus 12. So 41, 25 plus 12. So that would be 78 minus x equals 69. And then if we move the x across, we get 78 minus 69 equals x, which gives us 9, which is the same. So as we bring this lesson to a close, I actually want to suggest that there's two methods. The other way we could do it, and you can choose whatever method works best for you, is you could make the central part an x and then go 41 minus x to work out the other region, because you know it's got to add to 41, and then this one 25 minus x. It takes a bit longer, but it's possibly maybe a little bit easier for some of you. Otherwise, you can just see how much do you need to have in the region, how much bigger is it, and then what's the difference, and 66 minus 57 would just give you 9, which is the same answer. All right. Are there any questions before I bring the lesson to a close? I think we've done quite a lot today. Any questions or comments or things you want me to clarify? Okay. Well then, Lebo, if you could put the poll out to the students. We still have 5 minutes left, so please do feel free to ask a question if I went a bit quickly or you're unsure of something. But otherwise, we'd love you to answer our poll, and yeah, we'll go from there. Cool. Any questions?
Sorry, I have a question. I was wondering. Sorry.
It's fine.
All right. I was just wondering, with is there another way you could work out the middle by using the formula for the one where you use M or
identity,
H, and then just for that you minus the 12?
You could, you could say you don't know. So when you do that, you would have to say M or H, and you know that M or H would be 69 minus 12, which gives you the 57.
Yeah.
Yeah, you can do that. And then you would say, well, what is the N of M? It's going to be 41. What is the N of H? It's going to be 25. And then you use the identity to figure out what the N of M and H is.
Yeah.
That you absolutely can do that. That's also fine. Yeah.
Okay, cool. Thank you.
There's so many ways to do it. I just try to kind of show you two of them, but yeah, as long as you're getting the same answer, it's all good.
Okay.
Cool. Inam, what can I do for you?
For all probability questions, can you use the Venn diagram method?
So not all probability questions. So there are three main tools we use to do probability questions. There's Venn diagrams, there's tree diagrams, and there's tables. And so those are the three main structures. These next two lessons are mainly on Venn diagrams, but we always come back to that formula, like what is the number of possible outcomes? What is the number of favorable outcomes? That's really the glue that holds this whole section and topic together. Does that make sense?
Yes, sir. Thank you, sir.
Pleasure. All right, my people.